Hi, welcome to this workshop. My name is Fabien Ferrero. I am professor at Université Côte d'Azur, and I'm working at the Laboratory of Electronics, Antennas and Telecommunications. Before starting this workshop, I would like to thank a lot the Things Network to organize this virtual conference. My workshop will be about antenna tuning for your LoRaWAN device. You can find all the slides about this workshop on this link. And this workshop is also supported by Lacuna and Everything's company. Here is the outline of the workshop. I will start by presenting why do we need to tune antenna. Then I will present the method we are going to use, which is based on the vector network analyzer, and the particularity here is that it's very low cost. Then I will present the antenna we are going to tune, which is an inverted F antenna. And then I will present and show the tuning of two different antenna. The first one is a miniature inverted F antenna with the UCA shape. And the second one is an antenna which will enable you to communicate with space with the Lacuna constellation. And I will finish by a conclusion. So before starting on the tuning, it's important to understand what are the key performance indicators for an antenna. So first, we have to define here a source, which is most of the time 50 ohm, which is going to provide a power to the antenna. So this power will be PS. A part of the power is not going to be accepted by the antenna because the antenna is not perfectly 50 ohm. So a part of the power is going to be reflected, and a part of the power is going to be radiated by the antenna. And usually this is exactly what we want. So the classical antenna performance indicator are first the reflection coefficient. We call it also S11 because we are using only one port. It's usually plotted in dB scale, and usually we are targeting a criteria between -10 and -6 dB. Then a second criteria is the total efficiency of your antenna. This criteria will include both the matching and the radiating losses. It can be also plotted in linear or dB scale, and basically it's just the ratio between the radiated power and the power from the source. And last but not least, you have the gain. So the gain is going to include both the matching radiation loss, but also what we call the directivity. So it's a principle that an antenna can be able to focus the radiation in some particular direction. Okay, normally it's plotted in dBi because you are using an isotropic antenna as a reference. This is not it's not going to be the focus on this workshop. We are going to mainly focus on the S11. Now we can have a look why it's very important to tune antennas. So antenna first is a resonance structure. So input impedance is changing with frequency. So meaning that your antenna is going to work only on a limited frequency bandwidth. And especially when you are looking to miniature antenna, usually we consider that it's a trade-off between the efficiency, the size, and the bandwidth, meaning that if you want to have a high efficiency and small antenna, it's going to have a narrow bandwidth, and then it's going to be hard, or at least you have to be very accurate on the tuning of the antenna. Second point, antenna is an open structure, meaning that compared to classical electronic components, antenna is strongly influenced by surrounding environment. So for an integrated antenna, the electromagnetic wave is generated both by the antenna and the terminal ground plane. So anything which is in the vicinity of the antenna or on the ground plane is going to change or to affect the way the electric field and magnetic field are placed, and so it changed the resonance frequency. So small antenna have to be very carefully tuned. Okay, so now we can move to the second part of the workshop, which is a low-cost vector network analyzer. So what is a vector network analyzer? I would say that the VNA is the RF engineer best friend. It enables you to measure both the reflection and transmission parameters at RF frequencies. So for example, if you look here, you can see that you are able to measure the reflected wave on a single port, or also the transmission coefficient between two ports. And you can measure both the amplitude and the phase of the signal. This type of equipment must be calibrated, and the price for professional equipment range from 10 to 30 kilo euro, depending on the number of ports and the maximal frequencies. So of course, if you have not 10K to spend in this type of equipment, what can you do? Basically, very recently, we can find some nano VNA. The price is from 30 to $100. So of course, when you compare with the professional equipment, it has limited performance. So especially, you have just a 50 dB of dynamic. It's battery powered. It needs also to be calibrated. You have also some limitation because you can only measure the S11 and the S21. But for antenna measurement, basically it's enough, and this is what we are going to see. So you can see here two different nano VNA. So you can see that you can find it with two different size. This one is the bigger one, so you can see the two SMA port here. Here you can change, tune the marker or change the mode. And the second one, it's more tiny, it's smaller, but it's the same thing. You have two ports. You can basically change all the mode, the frequency of the marker, and it's a touch screen, so you can set everything you need. So when you want to select your nano VNA, pay attention, several versions are available. Initially, the maximal frequency was 900 MHz, which is okay for Europe, but not okay for US. But now you can find a nano VNA that can go up to 1.5 GHz. Of course, you have the two screen size, but the 2.8 inch is lower cost. You have a code which is open source available on this link, and you can change the firmware of your nano VNA, and you can also connect your nano VNA to a computer using the USB, and then you can visualize on a big screen the result. And then also, last point, nano VNA 2.0 is under development, and it will be able to range up to 3.5 gigahertz, which would be good, especially if you want to tune GPS or Bluetooth antenna or LoRa 2.4 gigahertz. So for any vector network analyzer, you need to calibrate it before using it. So the calibration is quite simple. You need, in fact, to connect three different loads, which are going to be open, short, and typically 50 ohm. So you can use SMA connector. So usually when you purchase this nano VNA, a kit like this is provided. But if you are using a small connector like UFL, it's also possible to, or you build yourself your own kit, or you can also find this type of RF demo kit where you can find the short, open, and load here. And so you can calibrate with a very small UFL connector. So the first thing that you need to do before starting the measurement is to choose the frequency band you are going to measure. So first you click on stimulus, and then you are going to choose the lower frequency, so click on start, and here we are going to select 800 megahertz. So you can see that the touchscreen is quite good, okay, but use a pen, it's easier to use it. Then we are going to define the maximal frequency. So you click on stop, and here we are going to choose 960 megahertz. Okay, and then we can start the calibration. So to start the calibration, we are going to come back, click on calibrate, cal, okay, and we click on calibrate. Okay, so then you can see that the three first buttons are open, short, and load. And you have also the through, which is for the two-port calibration. So before starting the calibration, you can see here that I have here an open circuit, and the reflection coefficient I measure is minus 21, which is not good because normally an open circuit should give you 0 dB of reflection because all the power is reflected by an open circuit. So then we start the calibration. So we are going first to start with the open circuit. So you connect open circuit and click on open circuit. Then we are going to remove the open circuit and we are going to put the short. So the short, you can easily find the short because you see that there is a connection between the signal and the ground. So we connect, and again we click on short, and the last load that we need to connect is the 50 ohm. So what you are going to see is that the 50 ohm one we are going to connect, we are going to change a lot the reflection coefficient, of course, because the reflected power is really low. So we gain here something like 20 dB. So we click on load. So of course here you see we are doing a one port calibration. We are just we have just the port 1 which is calibrated. If you want to calibrate the two ports, you will need also to have a second cable to connect the two ports together and to click on through. Okay, but even if you are going just a single port calibration, you can click on down and it's okay. So you see that now we have the 50 ohm is still connected, so we have a reflection coefficient about minus 40, which is good. Okay, and then now if we unconnect the 50 ohm, we are going to have an open circuit, and here you see that we have a reflection coefficient very close to 0 dB, which means that our VNA is calibrated. So we can now move to the antenna we are going to measure, which will be an inverted F antenna. So I'm going to use some simulation to illustrate the principle of the antenna. So here you have a very classical monopole antenna. So you have a ground plane and a quarter wavelength monopole antenna. So we are targeting 2.4 gigahertz. So you see that the total length of the ground plane plus the monopole is close to a quarter wavelength. Here you can see the Smith chart, and you have here the real part and the imaginary part of the input impedance. So when we have the resonance, so imaginary part is equal to 0, we have an input impedance close to 70 ohm, which is what the theory will give you for this type of antenna. But of course, this type of monopole antenna is not really acceptable for modern communication device because the antenna is too large compared to the terminal. So what we want is to have antenna which are very close to the ground plane. So what you can easily do is just to bend the monopole. So as you can see, we call it inverted L antenna. And now if you look at the reflection coefficient, you can see that we have not a very good matching. So especially if we look at the real part and imaginary part, at the resonance, now we have an real part for the input impedance, which is close to 10 ohm. Okay. So for RF engineer, it's not a big issue to have not a good input impedance because using some matching network, it's always possible to change from any input impedance to 50 ohm. So for example, if we look at the inverted L antenna, you can see that just by adding a shunt component, so if we add a shunt capacitor, we can easily move the input impedance to 50 ohm, or if you use a shunt inductor, okay, also we can easily move the input impedance to 50 ohm. So we can use passive component, we can also use stub. So what we are using with an inverted F antenna is exactly this principle. We are using a short shunt stub. So you can see here that now the antenna is directly shorted to the ground plane, and by doing so we are in fact adding an inductor effect in shunt, and we are perfectly matching the antenna. So we are not exactly at the right resonance frequency, but then we just need to adapt the length of the antenna to match it at the right frequency. So now we can move to the antenna tuning of the miniature antenna. So first, to introduce you this antenna, so it's a miniaturized printed antenna. Basically, it's using the logo of my university. But you can see that you have the feeding here, you have the short circuit here, and the current is moving like this. So it's like a meandered antenna to compact the size. So it's mounted on a 80 by 34 millimeter PCB with 0.8 millimeter thickness. And the performance is equivalent to a classical printed antenna. And if you are interested, you can find the layout, which is open source, on this link. So this antenna of course, is matched to 50 ohm. The bandwidth is about 30 megahertz. The radiation efficiency is minus 1.2 dB, so 75%. It has a radiation pattern of a dipole, so you can see here the radiation pattern. It's omnidirectional. And the gain the peak gain is about 1 dBi. So as I say, the antenna is printed on FR4 substrate. So you can see that there is a possibility to add a transceiver, LoRa transceiver RFM 895. And what is interesting for us, if you go on the bottom part of the substrate, there is a possibility to add a UFL connector. So as it is a miniature antenna, the bandwidth is limited. So for example, here you see the antenna is tuned for European band, but of course, if you target US or Asia bands, you will need to retune the antenna. And this part can be very easily done by just changing the length of the top line. So if you change here the cut in the top line, you are going to change basically the length of the antenna. So you change the resonance frequency. So by cutting the line, you can change the resonance frequency from 845 megahertz to 950 megahertz. So here is a simulation of the reflection coefficient when we cut the line, so you can see that you can very easily tune your antenna. To connect the antenna, we are going to use a small UFL connector. You can see that it's very small, so the impact on the antenna will be negligible. But of course, if you have not the place to put a UFL connector, you can also directly solder a coaxial cable directly on the feed of your antenna. So now we can move to the tuning of the UCA antenna. Okay, we are now ready to start our measurement. So you see that I solder the UFL connector and I plug a coaxial with a SMA connector at the end. So I just need then to use support. So it's better to use a support made of polystyrene or foam support because it's mainly made of air, so it will not influence your antenna. So now we connect the antenna to the VNA. We put the antenna on the support, and as you can see, we have a beautiful resonance at 849 megahertz. So here you can see I solder a piece of soldering to close the gap, so this is why the frequency is slightly lower. As I already mentioned, antennas are very sensitive to the environment. For example, if I put my hand very close, you see that I can easily shift the resonance frequency. So this is why it's very important to tune your antenna considering every object or every component which is close to your antenna. Another example of effect from the environment, if we remove the support, the foam support, and we place it directly on the table, you will see that the resonance frequencies shift down. So we move to 800 megahertz. Why? Because the wood has higher permittivity compared with the air, so it's shifting down the resonance frequency of the antenna. Okay, it's now time to tune the antenna. So I can remove the piece of soldering which was closing the gap. So it's a first try, so it don't change. Okay, second try. Again, solder iron. Try to remove the soldering from the gap. Okay, and then it worked. Okay, so then you see we move the resonance frequency to 900 megahertz. And now we can measure the frequency bandwidth of the antenna. So by using the cursor, we can look at the maximum frequency with a -6 dB reflection coefficient, and same thing for the lower frequency. And from that, we can find that we have a frequency bandwidth of 35 MHz, which is correct with the simulation. Just to show that we can again tune the antenna, so if I cut the line with a scissor, then you see that the resonance frequency now is moving to a higher frequency, so it's moving close to 925 MHz, which is good for communication in US and Asia. So it's very important to understand that when you want to tune your antenna for a particular application, especially when you have battery, plastic casing and so on, it's important to make the test with everything around your antenna. For example, for this project, I test both the LoRa antenna and also a GPS antenna. So we can move now to the Lacuna space antenna tuning. For space communication, we need to generate a circular polarization. And to do so, what we are using is a Tri-fillar configuration. So we have three inverted F antenna. You can see the first one here, the second one here, and the last one here. And we have a special circuit to generate a 120-degree phase difference between each antenna. You can see that the antenna is quite compact. It has a maximal dimension of 70 millimeter, and the height is about 12 millimeter. So here you can see a picture of the antenna, and you can see that we are using a UFL cable to feed the antenna. So here you can see the beautiful Tri-fillar antenna, so the three inverted F antenna. So we see that behind we have a UFL cable, and the antenna has been designed and manufactured by RFthings. Okay, it's now time to connect the antenna. So I'm using a UFL to SMA connector to plug the antenna to the VNA. So we have a very characteristic reflection coefficient. As you see, we have a double dip. You can consider that we have the maximum gain at the top between the double dip, and here it's 865 MHz, which is very good for this application. We have a bandwidth of about 30 MHz, and you see that the antenna is still very sensitive to the environment. If I place my hand close, you see that it's changing a lot the reflection coefficient. So as the antenna is composed with three miniature inverted F antenna, it's very important to fine-tune all the antenna depending on the environment. For example, we design a casing. If we play the casing on top of the antenna, the resonance frequency is shifted down. So you can see that now we have a resonance frequency close to 827 MHz. So of course, if I want to use this casing, I need to tune back my antenna to get an optimal performance at my target frequency. To tune this antenna, we have several options. For now, on the actual prototype, we can use zero-ohm resistor. So you can see that you can just solder or unsolder the zero-ohm resistor. On the future version, we'll have just a simple line with the solder mask which is open, and then you can be able to directly cut the line at the exact dimension that you need. So I'm going to show that we can tune. So as you can see here, you can see the small 0-ohm resistor on the antenna. So here you can see I'm unsoldering every resistor. So I'm going to change typically the line of the length of the line of the antenna. So now if we measure again the reflection coefficient of the antenna, you can see that it has been shifted up as expected, and it's very close to 925 MHz, which is what we target typically for US and Asia bands. Okay, so it's now time to conclude. Okay, so what we saw in this workshop is that you need always to test and to tune your antenna. You should never trust any datasheet. NanoVNA is an affordable solution with sufficient performance for antenna tuning. The VNA is a useful tool to tune your antenna, but be careful to the cable effect. Try to place the cable in different positions to be sure that you have the same result. The VNA do not provide the radiation efficiency, which is an important criteria for the quality of your antenna, but to estimate the radiation efficiency, you need to perform a radiation test. Normally, you need an anechoic chamber to do it, but last year, I make a presentation on a low-cost solution, and you can find all the information on this GitHub link. So thanks a lot to attend to this workshop. I hope that you enjoy it. And I would like again to thanks a lot the Things Network to organize this amazing virtual conference. So if you have any question, feel free. I will be at the chat, or you have also my email. So feel free to contact me. I will be happy to try to help you. Thanks a lot. And just to conclude, I have a special thanks to my daughter, Constance, who lent me her office desk to make all the video you have been seeing today. So thanks a lot, Constance, for letting me using your desk.